Good morning, everyone. In today's video lecture, we'll learn about principle, process, and applications of affinity chromatography. So let's start. Chromatography is widely used laboratory technique for the separation of components in a mixture based on their differential interactions with stationary phase. This technique aids in the identification and purification of components and is applicable for both qualitative and quantitative analysis. So affinity chromatography is a type of liquid chromatography which utilizes the reversible biological interaction between components in the mobile phase and solid stationary phase for separation. So in affinity chromatography, usually its principle is basically affinity. Okay, so affinity between components and the uh, mobile phase or stationary phase. Okay, so this is the basic principle. It was discovered by Pedro and Mayer in 1968. Affinity chromatography falls under the broader category of adsorption chromatography. So, we know GFC, I mean gel filtration chromatography, affinity chromatography, uh, ion exchange chromatography. These are some kind of adsorption chromatography because here adsorption takes place. However, it is highly specific and selective in comparison to adsorption chromatography. In affinity chromatography, the adsorption process is effective and specific, relying on the binding affinity between target biomolecule and ligand immobilized on solid support matrix. So this is the most specific and elective method because in this chromatography, usually a specific protein will bind with specific receptor. Okay, for example, if any antibody, you take any antibody as stationary phase, then only specific antigen will bind with this antibody. It enables the purification of target biomolecule based on their biological structure and function. Some ligand target interactions include enzyme substrate, it can be enzyme inhibitor, antibody antigen, lectin glycoprotein, etc. Ligands obtained from biological sources include antibodies, enzyme, protein, glycoprotein, and others. Synthetic ligands used as metal chelates, boronates, biomimetic dyes, etc. Prepacked columns such as high trap and high prep, etc., are commercially available, facilitating repeat optimization. So here we can see different components of affinity chromatography. Um, this is somehow different from our previous chromatographies like column chromatography, TLC, gel filtration chromatography, ion exchange chromatography, or any other protein chromatography. This is somehow very different because in this case, usually stationary phase is very selective. Uh, Stationary phase, like it can be antigen or antibody, whatever it is, and there is a ligand. Okay. uh, there is ligand and our target molecule bind with this ligand. So there is another thing, that is spacer arm. So spacer arm usually connects it with the matrix. Okay, so this is the basic stationary phase and this is the substrate. So we'll discuss one by one. First of all, matrix. Chemically and physically inert support that directly or indirectly couple a ligand. Matrix should have a relatively larger surface area for better ligand attachment. It must be insoluble in solvents and buffer used in purification process. Okay, so if it gets soluble with the solvent or buffer, then obviously it will just be washed out with them. It must exhibit good flow properties. For example, agarose, polyacrylamide, polystyrene beads, cellulose, etc. So these are usually used as matrix. These are some non-sugar polysaccharides. Now, this is a spacer arm. Actually, it acts like a bridge between the ligand and matrix. It connects the ligand to the matrix, employed to improve binding efficiency between the target molecule and ligand by overcoming steric hindrance. For example, 1,6-diaminohexane, 6-aminohexanoic acid, and 1,4-bis 2,3-epoxy propoxybutene. Okay. The ligand refers to the molecule attached or immobilized to the matrix, which reversibly bind to the specific target molecule. The selection of a specific ligand depends on the nature of the target molecules. For example, antigen is used as a ligand for antibody isolation, substrate or inhibitor is employed as ligand for isolation of enzyme. Ligands are can be classified in two types, like monospecific and group specific ligands. So monospecific low molecular weight ligands are the type of ligands that bind to single or small number of protein or target molecule, for example enzyme inhibitor, steroid hormones, vitamins. Okay, so ligands usually this will bind with substrate. Okay, then group specific ligand bind to the large number of target molecule, include biomimetic dyes, boronic acid derivative, 5-AMP, etc. So here are some ligand. Okay, and here are some protein of interest. Actually this protein of interest is our sample. You will apply a lot of samples or a lot of proteins, and within these proteins only those would bind with ligand. Okay, so whenever you are taking any substrate inhibitor or cofactor as sample, then your ligand should be enzyme. Then whenever you are taking antigen, virus or cell, then your ligand should be antibody. Whenever your sample is different polysaccharides, glycoprotein or cell surface receptor, then your ligand would be lectin. Okay, whenever your sample is histone, nucleic acid polymerase or nucleic acid binding protein, then obviously your ligand would be nucleic acid, because there should have some compatibility. Whenever your protein of interest is glutathione as transferase or GST fusion protein, then glutathione should be your ligand. Okay, so accordingly this example, just go through this. Just keep in mind that your protein of interest should be compatible with your ligand. Okay, you cannot use for example you cannot use any substrate or antigen for glutathione. Okay, or I mean you cannot use like lectin for RNA containing um, protein. Okay, you cannot use lectin for RNA containing poly U sequence. You should use poly A. Okay, so this is very specific. Okay, that is why in in your previous chromatographies you didn't see these sorts of interaction, but those are non-specific, because whenever you are undergoing different gel filtration chromatography, then yeah, different substrate or samples are getting separated by according to their molecular weight. Okay, it's not a problem. But yes, whenever two compounds are having same molecular weight, then they are just eluting same speed, so it would create some sorts of non-selectivity. That's why we use affinity chromatography for better specificity. Okay, so let's discuss the principle. Affinity chromatography is one of the most diverse and powerful chromatographic method for purification of a specific molecule or a group of molecules from complex mixtures. It is based on highly specific biological interactions between two molecules, such as interaction between enzyme and substrate, receptor and ligand, or antibody and antigen. These interactions, which are typically reversible, are used for purification by placing one of the interacting molecule, referred to as affinity ligand, onto a solid matrix to create a stationary phase while target molecule is in mobile phase. Many of the commonly used ligand coupled to affinity matrix are now commercially available and are ready to use. So this is basic principle of affinity chromatography. This is matrix, this is your ligand, and the main function of the ligand is uh, it will contain the substrate. Okay, so when your sample is coming, it is binding with the ligand. Okay, you can see the complex. So other impurities will just go out because it is not binding with the ligand, because this is very specific. Then after some time they will be loosely connected, because that need to be washed out. Okay, otherwise you cannot detect this, you cannot have the sample, purified sample. Okay, so after some mechanism we washed out this purified sample and we collect this, and yes, this is our purified sample. So that is how we purify, isolate or separate our protein. So other for example, you have a lot of proteins. Okay, these are some hexagonal. Just to think, this is the red are one protein, the green one is another protein which is circular, then another one protein, a lot of protein you have. Okay, now your antigen is very specific. Specific to what? Specific to the hexagonal shape protein. Okay, so whenever you are just loading your samples, your sample has a lot of protein, but you need one specific protein for purification or separation or isolation. So you just get this, then yes, only the protein which can bind with the stationary phase will bound. Okay, will bind with this, and the remaining one will get eluted. Okay, so after that will perform the elution, because it should not get attached to it for very long time. Okay, because it should be separated out, and we collect the purified protein by simple elution. So you can see the procedure has been shown here. This is protein buffer, this is the sample, because the buffer will act as mobile phase. Then we apply the sample, and within this, you know, only based on the selectivity, only those protein comes out. Okay, then finally, whenever we are applying the elution buffer, then the function of the elution buffer is obviously is to elute your desired protein. These are your some other proteins, this is your desired protein. So this is the basic mechanism. You can see here, actually buffer is playing a vital role. Okay, because you cannot use usual solvents. Okay, because protein is your sample, and you know, whenever protein is your sample, then you need to use buffer, because for maintaining proper isoelectric point or deuterium ions, etc., you need buffer. Okay, you cannot use like methanol, ethanol, acetonitrile. Okay, so there are now different types of protein based on their stationary phase or mechanism, like lectin affinity chromatography, immunoaffinity chromatography. Here, antigen antibody works. Then metal chelates chromatography, like EDTA calcium. Okay, dye-ligand chromatography, it works on the different dyes. Then covalent chromatography, a lot of chromatography. This is under the classification of affinity chromatography. Now we'll discuss factors affecting affinity chromatography. You know, you have ligand, you have matrix, you have substrate. Okay, you have a lot of things. You have stationary and mobile phase, a lot of things. Now we'll see how these components affect your separation or purification in affinity chromatography. First of all, ligand. There is some factors regarding to ligand, there is some factors regarding to the matrix. You'll also see some factors regarding the stationary phase, you'll see some factors regarding the pH or the buffer. Okay, so these are the usual factors. So first of all is specificity of the ligand. The ligand must be very specific, because within this ligand, with this ligand our substrate will bind. Okay, so there should be specific for the target molecule. Non-specific interaction can lead to pore separation. Then affinity or binding strength of ligand. Optimal binding occurs when the interaction is neither too weak or not too strong. Low affinity results in poor yields, since the target molecules might leak from the column or are washed away. High affinity also result in lower yields, as target molecule may not dissociate from the ligand during elution. Then nature of matrix. A physically and chemically inert matrix having higher surface area is preferred. The pore size should also be appropriate for the target molecule. Then pH. Optimal pH ensure proper binding of the ligand and target. Extreme pH can denature protein and disrupt of weaken the interaction. The nature of the buffer used. The buffer should maintain pH, ionic strength, and stability for both ligand and target molecule. Then flow rate. Optimal flow rate balances binding efficiency and processing time. So these are basically the factors which will affect the efficiency of affinity chromatography. So you know, chromatographic media, it plays a vital role. Okay, because you need to use some protein buffer, you need some elution buffer, loading buffer, okay, washing buffer, a lot of buffer you need to be used. So this media is will play a vital role. Just go through this, you can easily understand. Then immobilized ligand. Okay, I have already talked about this, just to go through this. So attachment of the ligand to matrix, so very important thing, because ligand, it works like a bridge. Okay, you know, you have stationary phase, and this stationary phase should be rigid. Okay, it should not be like that whenever you are applying some buffer solution, then your stationary phase is getting washed out. It should not be like that. So several procedures have been developed for the covalent attachment of the ligand to the stationary phase. All procedure for gel modification process into separate chemical steps, like activation of the functional group of the matrix and joining of the ligand to the functional group on the matrix. A wide variety of activated gel is now commercially available. The most widely used are described as following. Okay, I'll show this later. You can see antigen will bind with antibody, antibody will bind with antigen, then substrate will with enzyme, DNA with histone, hormone with binding protein or receptor. Okay, so these are the things we have already discussed. So let's discuss the uses of affinity chromatography, because it is one of the most selective and specific uh, chromatography ever we have discussed earlier. So purify and concentrate a substance from a mixture into a buffering solution, reduce the amount of substance in a mixture, discern what biological compound bind to a particular substance such as drug, purify and concentrate as enzyme solution. Limitation of affinity chromatography. For first of all, time consuming method, more amount of solvents are required which may be expensive, intense labor, non-specific adsorption cannot be totally eliminated, it can only be minimized, then limited availability and high cost of immobilized ligands, then protein can denatured if required pH is not adjusted. So these are some limitations. This is very sophisticated chromatography, because whenever any substrate is not binding with ligand, then it may be washed out, and proper separation may not take place, or proper purification may not be takes place. Okay, so it is very important. So there are some limitations, because as it is very sophisticated, so it is intense level, time consuming. Okay, moreover it should be very specific, it is also one of the limitation. So, however, there are some advantages, like high specificity target molecules can be obtained in highly pure state, then single step purification. The matrix can be reused repeatedly. The matrix is solid, can be easily washed or dried, give purified product with high yield. Affinity chromatography can also be used to remove specific contaminants such as proteases, then expensive ligand, okay, leakage of the ligand, degradation of the solid support, limited lifetime, non-specific adsorption, relatively low productivity. Okay, so let's see some applications. As I have also discussed this in previous tables. For example, it is for isolation and purification of all biological macromolecule. It is used to purify nucleic acid, antibodies, enzyme, to notice which biological compound bind to a particular substance, to reduce amount of substance in a mixture, used in genetic engineering, nucleic acid purification, production of vaccines, antibody purification from blood serum, and basic metabolic research, protein or enzyme purification from cell-free extracts. So these are the applications of affinity chromatography. So here I have shown some common products and manufacturers of affinity chromatography. Commercially available products and their manufacturers. Just go through this. So this is overall from our lectures on affinity chromatography. If you have any confusion, please inform me in the comment section. Thank you.